Hello and welcome to another lecture in the course. So we're going to look at Laplace transforms of derivatives and how to use them, how to use Laplace transform to solve ODEs. So this is section 6.2 in the book, part 1 of the section 6.2 in the book. You can get the book on this link. You can browse it on the web, get a PDF, or you can even buy a cheap paperback version. All right. So to solve a differential equation with Laplace, we need to know how do derivatives transform. If I have a function and if I take its derivative and I take the transform of that, what do I get? How does it relate to the transform of the original function? So suppose that I have a function g, and let's suppose it's a differentiable function. So I have a derivative and it's of exponential order, which really is this thing that the function, the absolute value of the function does not grow too fast. It grows something like an exponential. So for large t, it's some constant times e to the ct. So m and c are constants, and so you get this inequality. And so we saw last time that says that the Laplace transform exists, at least for s bigger than c. And we also get that this means that if s is large enough, if it's bigger than c, then we get that. I mean, g itself might not go to 0, but if I multiply by e to the minus st, then st goes on to infinity. E to the minus st times g, that goes to 0. All right. So let's look at the Laplace transform of g prime. Let's see what happens there. So the derivative of g. Okay, well, let's just plug it into the definition of what that means. This just means this integral, right? And it's a function of s, right? So s, s it's a variable, but not as far as the derivative is as far as the integral is concerned, right? So we're for some s, we write this integral, and it's going to be important that the integral is in t, not in s, right? Now, if we have this, what we could do is we could do integration by parts. To get to this expression over here. So we get the boundary terms over here, right? And then we get this. We basically take the derivative from the g and put it on the exponential, right? So notice how when we differentiate the exponential in t, right? Because the integral is in t, in terms of t. S, as far as the integral is concerned, s is a constant, right? And it's sitting up there in the exponential. So when I differentiate the exponential, the s, or the minus s, comes out, right? By chain rule. And of course, the derivative disappears over here, right, on the g. So, okay, now this is really, this is really an improper integral. You want to think of this in terms of limits, right? Limit as, the upper limit goes to infinity. Now, we notice something because of this, right? As long as s is bigger than c, and we're really thinking of this for large enough s anyway. So then at infinity, this thing just goes away, right? So we're really just looking at this at 0. So we get minus g at 0, whatever that is. I mean, some value. And then over here, what happens with this term is that, well, this minus sign cancels out this minus sign. And this s, well, if you remember, s is just a constant as far as the integral is concerned, right? So the s just goes out, right? So what we get is the s actually comes out of the integral, right? So it comes out of the Laplace transform. So we have, what's left is the Laplace transform of G, right? So we got this line in this table. When we have G prime, then it's S times the Laplace transform of G minus G at 0, right? Now, we can repeat this procedure, right? And so if we have G double prime, well, G double prime, that would be the same thing as S times the Laplace transform of G prime minus, G prime at 0. And we just apply again, right? And we get this formula, right? So that's just applying the same formula twice. Oh, you could do it 3 times or 4 times or 5 times. You can do it as many times as you want. We're really mostly just going to think of second order. So really, these two lines are the important ones. Well, or really just the first one. You can figure out the second one from the first one, right? So what happens is that you're multiplying by S. Now, the key thing is that the Laplace transform of G does not get differentiated. It gets multiplied by S. The other feature is that you can see the initial condition over here, or well, initial. It will be the initial condition for us later on. I mean, it's the value of the function at one point, at the point 0, right? So, all right. So let's use Laplace transform to solve a simple equation. So, I mean, you could complain that we can solve this in other ways, for example, undetermined coefficients, but let's just humor ourselves. Let's solve it with Laplace transform to see how this simple example works so that we can go to more complicated examples later, right? And we're going to put these initial conditions on this equation. All right. So this equation, right? I mean, it's some function of t equals some other function of t. What's on the left-hand side is the same exact function as what's on the right-hand side, if we have a solution, right? So we take a Laplace transform of the left-hand side and the right-hand side. Well, if those are the same function, their Laplace transform should be the same functions, right? So that's that equation over here. So let's write it out, what that is. So, well, we have a formula, right? I mean, the Laplace transform is linear, so I can just take Laplace transform of x double prime. That's this guy. The Laplace transform of x. That's this guy, right? Add them together. And the Laplace transform of cosine of 2t is this. All right? So now let's plug in the initial conditions, right? Because you can see the initial conditions coming up here, right? So x at 0 is 0, so this guy is just not there, and this becomes minus 1, right? That's where that goes in. And so now we have this equation in capital X, and you can notice there's no more derivatives, right? We can solve this for x, for capital X, right? We just use high school algebra to solve this, right? So we solve, right? We put the plus 1 on the other side, right? And then you pull out the x, and you're gonna have s squared plus 1. You divide. Anyway, however you do it, this is what you get, right? So that's what capital X of s is. Now we're not done yet. We have a function of s, right? So we have the Laplace transform of the solution that we're looking for. So what we need to do is now we need to undo that, right? We need to get little x, right? So first, well, I know how to do the inverse Laplace transform of this guy. That's easy, right? That's fine. But this guy, well, that requires a little bit of work. So you have to do, for example, partial fractions. So you change this into this, right? Using partial fractions. And all right, so now we have a formula for x, which we can easily just look at the table of Laplace transforms and write down the inverse Laplace transform, right? This guy is cosine, this guy is cosine of 2t, and this guy is sine, right? So now we have little x, right? Okay, easy peasy, right? So the whole thing was you take the equation, you Laplace transform everything, solve this algebraic equation, right? There's nothing is easier than that, right? And then you have to do the inverse Laplace, right? So the forward Laplace and the inverse Laplace are usually the hard bits here, right? In this case, it was easy because we had an easy equation, all right? So this is the procedure for constant coefficient linear ODE. So you transform the equation. You use these rules to transform the where the variable, the dependent variable appears, right? You put in the initial conditions, right? If you don't have them, then these are unknowns. You solve for capital X, and you compute the inverse Laplace transform, right? And that's your solution. Now, this only works, obviously, when you can take the Laplace transform of everything in sight, right? Everything that appears, you have to be able to take a Laplace transform of, right? Namely, the left-hand side and right-hand side. You have to know how to take the Laplace transform. So, for example, if the right-hand side is tangent, let's say, then Laplace transform won't do any good because there's no way to take the Laplace transform of that. But it actually works for, it is useful, right? It's useful for things that we don't know how to solve yet. So, don't think that this is just, I'm telling you that you can't solve any useful equations. Actually, most of the equations that are useful, you can be, or maybe most, but a lot of equations that are useful can be solved using Laplace. It's a very common technique. So basically, I mean, as long as you have constant coefficient, linear ODEs, it's really just the right-hand side that's tricky. Now, the Laplace is actually very good at solving a lot of right-hand sides, a lot of these inputs. You think of this equation as being sort of input. The right-hand side is the input. The solution is the output. A lot of inputs that come up in applications. For example, something that the other techniques that we looked at can't handle are things that are defined piecewise, right? Your input is going to do something for a little bit, and then something else for a little bit, and then something else for a little bit. Laplace is going to have an easy time of doing that. So if you can construct your input piecewise from simple functions, then Laplace is actually going to be pretty good at handling it, right? And this is where the Heaviside function that we looked at last time comes in. So that's the function whose, that's not what I wanted to do, whose graph looks like this, right? It's 0 until you hit 0, time 0, and then it's 1 from then on, right? And it's usually used shifted, right? So that it's 0 until time is a, whatever a is some fixed value, and then it's going to be 1 from a onwards, right? So how do we use it to write down piecewise defined functions? Well, let's do a simple example. Suppose that I have something, I have a function that's 0 until pi, and then it becomes sine, right? So it's basically sort of like a delayed sine signal, right? It's 0, 0 until pi, and then suddenly becomes sine, right? Well, we could write it using the Heaviside function just by, well, we take sine, that would be sine everywhere, but we multiply it by the shifted heavy side, shifted by pi units. And so this guy over here, right, the heavy side is just going to be 0 all the way up till pi. So I'm multiplying by 0, so everything is 0, right? So as long as t is less than pi, this f of t is just 0, right? Which is exactly what I want. And then when t is bigger than pi, well, this heaviside part of it is 1, right? So I'm just multiplying the sign by 1, so I just get sine, right? So it's precisely this thing, right? So that means that I've written this sort of piecewise definition using the heaviside function, using sort of a nice single formula, as long as I put in the heaviside, right? All right. Now, maybe something a little bit more complicated. Suppose that I have, well, what if I have this rectangular pulse, right? That I have a function at 0 everywhere, except it's going to be 1 at on the interval from 1 to 2, and then it's just going to be 0 again, right? So it's this pulse, right? It's 0, 0, 0, 0, 0, then 1 for a little bit, and then 0, right? Well, I could just build it up out of heaviside functions, right? So this guy, if t is less than 1, then both the first term and the second term are 0, so I get 0, right? When t is between 1 and 2, then this first term is 1, and the second term is 0, so it's 1 minus 0. That's 1, right? And when t is bigger than 2, well, they're both 1. So it's 1 minus 1, it's 0, right? So this is precisely that function that we described, right? Now, that sort of idea can be useful for defining piecewise functions that are a little bit more complicated. So suppose that I have a function that's supposed to be t on the interval from 0 to 1. It's supposed to be minus t plus 2 on the interval 1 to 2. And it's supposed to be 0 otherwise. So it's supposed to be this function that basically has that little, it's the graph looks like a little triangle, but it's 0 everywhere else, right? So outside of, if it's less than 0 or bigger than 2, I'm supposed to get just 0, right? Well, what we could do is we could use this sort of an idea, right? Actually, we're gonna use that idea over here, right? But let's start at the beginning. So we have we're supposed to have t when t is between 0 and 1. So I take this function that's 1 exactly when t is in this interval, and I multiply it by t, right? So this first term over here, it's precisely going to be t on this interval and 0 otherwise, right? Now, let's look at the second line, right? So now we have, I want this guy that's 1 exactly on this interval from 1 to 2, and I multiply it by what is supposed to be on that interval. And this whole term is 0 otherwise, right? So on this interval from 1 to 2, it's precisely minus t plus 2, and it's 0 otherwise. So when I add these two, I get precisely this function, right? When t is less than 0, then both of these are 0. When t is between 0 and 1, I have that this second term is 0, and its first term is t, right? When t is between 1 and 2, the second term is minus t plus 2, and its first term is 0. So I get minus t plus 2. And I get 0 otherwise, of course. But so when t is bigger than 2, then both of these guys are 0. All right. So how do we, how does this interact with Laplace transform? Well, this is the second shifting property, and you can derive this out of just the definition, right? If you write down the definition, you play around with it a little bit, you're going to get this rule. So you can derive this rule just from the definition of Laplace, just like the first shifting property. So basically, what it says that if I have a function and I write it as a function of t minus a, right, times the Heaviside function of t minus a, then it's the same thing as multiplying by e to the minus as. The Laplace transform of f now is just a function of t, right? So let's see an example of this in action, right? So let's suppose that I just look, this is one of those things that's going to be like one of the terms over here. If I have if I expand this first, guys, I'm going to have t times u of t minus 1, right? So how would I take the Laplace transform of this? Now, you can see that it doesn't quite fit into this mold, right? I have t times ut minus 1. A is clearly 1, but this t is not written as a function of t minus 1. Well, but, I can just make it as a function of t minus 1, right? I just rewrite t in what seems like maybe a stupid way, but it's to make it fit into this side of the formula. It's t minus 1 plus 1, right? And then it's a function where I'm plugging in the argument as being, it's the argument into the function plus 1, right? And so the argument is t minus 1, right? And so now I have a function of t minus 1, right? So my f of t would be t plus 1, right? And so if I plug in t minus 1 into that, I get t, right? All right. So now into this thing, I can plug that into this formula. So what we have is e to the minus s, a is 1, right? Times the Laplace transform of t plus 1, that function that I just got here, right? And well, we know what the Laplace transform of t plus 1 is. We just look at the table and we get this formula, right? So this is the way that we use the second shifting property to transform functions like these, and therefore functions that are written piecewise. And this is something that Laplace is very good at, right? And you can see that it's, here we had to write this thing as was a piecewise formula, and now I have this wonderful, wonderful equation here. All right. So let's consider, something with a piecewise right-hand side, and let's do really simple piecewise right-hand side. So let's suppose that I have this mass spring set up, and let's do very simple initial conditions for simplicity, just zeros, right? And let's suppose this right-hand side is going to be 1 if I'm in the interval from 1 to 5. So between 1 and 5, it's 1, otherwise it's 0. So it is this rectangular pulse function, right? So for example, you could put a rocket motor attached to the mass, and it's fired, for 4 seconds, starting at t equals 1, so until t equals 5, and then it's turned off, right? Or perhaps if you have an RLC circuit, so it's not a mass spring, it's an RLC circuit, then the voltage is being raised at a constant rate for 4 seconds, and then held steady again, right? So some setup like this, right? Basically, where the right-hand side is this piecewise function, right? So we write this piecewise function using the Heaviside function, right? And then we transform the equation, right? So we have this guy, we transform, we get this, right? So, here we didn't have to use the second shifting property. We actually had, this was in our table, but it is actually using the second shifting property as well. If you think of the second shifting property, we're multiplying by a constant, right? But either way, you get this guy, right? You solve for x, so you get this. Okay, now we have to figure out how to take the inverse Laplace transform, and now it has these exponentials in there. So here is where we will use the second shifting property in reverse, right? Because we have something that looks like what could have been gotten by a second shifting property, right? Because it's some nice rational function, 1 over s times s squared plus 1, right? And the whole thing is multiplied by either e to the minus s or e to the minus 5s, right? So let's look at just this guy without the exponential. And I'll, this is an exercise. I'll let you figure it out. You do partial fractions, and you'll get that the Laplace, the inverse Laplace transform of that is just 1 minus cosine, right? Or conversely, the Laplace transform of 1 minus cosine is the thing that we want, right? So now we have, what we will plug into the second shifting property to get inverse Laplace transform of x. All right. So that's what we're doing here. So if we're taking the inverse Laplace transform, what the second shifting property is telling us is that, well, it's e to the minus s. Well, it is not yet the inverse Laplace transform. Sorry, it is not yet the second shifting property. I'm gonna apply it just in a moment, right? I've just rewritten this thing, right? So it's e to the minus s times the Laplace transform of 1 minus cosine of t, which is 1 over this thing, right? Now this is the equality that the second shifting property tells us. It's that function, right? Shifted t minus a. A is 1, right? Because it's minus 1 times s, right? Times u t minus 1, right? So that's why I'm getting this thing, right? It's this function with t minus 1 plugged in and multiplied by u t minus 1. So this is where I get the a, right? Now, similarly, for the other guy, again, I write it like this, right? And now I can just, now I can apply the second shifting property, right? So here, the a is 5, right, in the formula, right? So I plug in, for this t, I plug in t minus 5, and I multiply by u t minus 5, right? So again, this is just the second shifting property, right? So, all right. So because x is the it's not a sum, but it's a difference of these two guys. When I take the inverse Laplace transform, it's the difference of these two guys. So it's this formula, and here is the graph of this, and you can see that it's for a little bit nothing is happening, then something starts happening, and this first first bit of the graph is different from the rest, right? Once you go past 5, it kind of stays the same. It's this sort of sine wave, but the beginning is just a little different, right? And that's because that's when that rocket motor is being fired, right? All right. So we'll look at how to solve ODEs a little bit more and how to actually solve some other equations. Next time to when we finish 6.2. All right. So see you then.